Hi all, in this lecture we will see the analysis 2. So we are going to see the RL series circuit. In the first analysis or analysis 1 we had seen RC series circuit, but in this one we will see RL series circuit. So resistor and inductor are connected in series together with the voltage source, and also of course we have the switch K, or we can also call this as a switch S, because I do not use the term yes because we use this yes everywhere in this S domain. So I use the notation called K for the switch. So we assume the switch is closed at the time moment t is equal to 0. Then immediately when t is greater than or is equal to 0, there will be some value in this voltage source. So that is V times U of t. So we assume the unit function. So now I have to write the current flowing through this loop, closed loop, I of t. So first I have to use the KVL. So KVL, so V times U of t, that is nothing but the source voltage, is equal to all the voltage drops occur in this loop. So R times I of t, so R is the resistor value, I of t is the current flowing through the resistor. So R times I of t plus L times di divided by dt. Okay, so now I have returned the algebraic equation in time domain for this circuit or for this particular loop. Okay, now I have to apply the Laplace transform. Remember, in the we are actually applying Laplace transform in the circuit analysis. So that's why now we are using the Laplace transform in this equation. So after I apply, now this V times U of t will become V divided by capital S. We just assume this is a constant. So so 1 divided by S. V as a constant we are keeping here, and 1 just as a constant. So it will become 1 divided by S. So V divided by S is equal to R is a constant. We are taking it, and then I of t will become capital I of S, and plus, so L is a constant we are just keeping, and then the di divided by dt, when you apply the Laplace transform, then it will become like this: S times I of S. So Ls times I of S minus, now I have to also consider the initial energy source of this inductor, so minus I of 0 minus. So this is the equation after we apply the Laplace transform. So again, now, if I assume the initial condition in this inductor is equal to 0, this one, then we can always remove this one whenever we assume initial condition is equal to 0. Okay, so then we can rewrite the same equation like this: V divided by S is equal to R times I of S plus Ls times capital I of S. So here I of S is common, so I just take it outside of the bracket. So I of S times, with a common bracket, R plus Ls. Okay, so I am always after the current I of S because that is my goal here in this circuit analysis. I have to find the current flowing through in this loop, right? So capital I of S, because now we are in the S domain. After we apply the Laplace, now we are in the S domain. So I of S, I take this term to the right side. So V divided by S times this term. So S times R plus Ls. So now I can simplify this equation further. So V divided by Ls time R divided by L plus S. So it's very simple. What I had done is here, I just take the L also as a common here, common factor. So now yes, L both will is a common for this term. So now R divided by L. So then even though if I bring the L inside, then the R will not change. That's why we are taking the L outside. So R divided by L plus S. So I just rewrite this equation in this way. This is just a standard mathematical simplification. Okay, so now what I have to do is I have to divide both numerator and denominator by L. So V divided by L, and here also I divide L. So then this L will be gone. So S times R divided by L plus S. Because I always have to do this to simplify the equation. Then only I can apply the inverse Laplace transform. So now this is the equation I have. So this is the equation we got from the previous page. So capital I of S is equal to V divided by L divided by S times R divided by L plus S. Okay, so now I have to rewrite this equation a little bit differently. So what I'm doing here, so the same equation I am writing with a partial fraction method. This is another mathematical term. Maybe you have studied already. If you haven't studied, just to follow this, then you will understand. So I am writing this A divided by S plus B divided by S plus R divided by L. So I have written this. I call this as a equation number A. So now I have to simplify further, right? So what I have right now. So I am just taking this V divided by L is equal to. So I am just making this S plus R divided by L here, and then S is here. So I am multiplying here, and B times S. So I just use this equation again in the partial fraction method, and then B divided by L. Again, I simplify this equation. AS plus R divided by L times A, and then BS we already have. So here you can see A is common. So I am taking A as a common. So yeah, AS plus A times R divided by L plus B, yes. So here, sorry, in this term and in this term, S is a common. So I take this S as a common. S times A plus B plus A times R divided by L. This V divided by L in the left side is as it is. Okay. So now I wrote the same equation in little more in a different way. So again now A plus B is equal to 0, I assume. Then I have to use this formula. So if A plus B is equal to 0, then what will happen? Then this term will be gone. So then V divided by L is equal to A times R divided by L. So here it is like this. So A times, so now I only want the A value. So then I have to take this R by L to this side. Then it will become reciprocal. So V divided by L times L divided by R. So L and L will be cancelled. So V divided by R. So now I got the value of A because I used this variable here, right? A and B. So now I find the value of one variable. A is equal to V divided by R. So now I can apply this in this equation. A plus B is equal to 0. A value is V divided by R, right? Then B value is equal to minus V divided by R, because here V divided by R plus B is equal to 0. So B is here. I take this term to the right side. So then it became minus V divided by R. So now I know both variables A and B values right now, because here first I just only assumed, I brought these two new variables into this equation. Now I have found the value of these variables. So I'm going to apply these variable values in this equation A. Then how the equation will become? So we know the left side of this equation is V divided by L, the whole divided by S times S plus R divided by L. I write the same thing just here again. And here A and B, I have the value. A is V divided by R, B is minus V divided by R. So I just use this, and then again I have to do some mathematical simplification of the same equation. So then what will happen? It will become, the equation will become like this. Capital I of S is equal to V divided by R times 1 divided by S minus 1 divided by S plus R divided by L. So this is a very simple way. What I did in this simplification. So remember this equation, this is nothing but I of S. So I just write the same I of S here, here, and this equation I take the V divided by R as a common outside, and then within the bracket 1 divided by S minus 1 divided by S plus R divided by L. I didn't do anything special. This is just a simple mathematical rewriting. Okay, so now this is the final equation in S domain. for RL series circuit. So this is the current flowing through this loop. Okay, now I have to apply the inverse Laplace transform and convert this equation again into the time domain. So now I have to apply the inverse Laplace transform. So inverse Laplace transform, what is the formula for the inverse Laplace transform? For example, if it's 1 divided by s plus a, we already know that. I told you in the previous analysis. So that is e to the power minus a times t, right? 1 divided by s plus a. Laplace, inverse Laplace transform of 1 divided by s plus a, it will become e to the power minus a times t. So here a is in this equation nothing but r divided by L. So v by r, that is constant, we are keeping it outside. So 1 divided by s, when you apply the inverse Laplace, it will become 1 and then minus, and here e to the power minus r divided by L times t. Yeah, a is nothing but r divided by L. So this is the final equation in the time domain again. So now we got both major equations. So this is the current equation in S domain, the final current equation, and this is the final current equation in time domain again. So now, yes, now we have solved this problem and we have completed the analysis of RL series circuit. So what we had done was we have written the first the KVL equation in time domain, and then we apply the Laplace transform and we have converted into like this, and then we applied some mathematical simplification. Also one more thing, in this equation I assumed there is an initial voltage in this inductor, but later I assumed there is no initial voltage, so I removed this or I ignored this term. So I have only this term, and then I have rewritten the same equation or did some mathematical simplification like this. And of course I have to use the partial fraction method using the hardcore mathematics. So I introduced two variables a and b, and then I have to find the value of this a and b, so using mathematics, pure mathematics. And then finally I found the equation I of s, this I of s, like this. And now I can easily apply the inverse Laplace transform and I convert back into the time domain. That's all about this analysis.